from taking notes. That's going to encourage you to add additional detail, star things, add pictures if it helps you. But I felt like a lot of this is review. There are some like little very detailed explanations of the solution process that dealing with like delta H 1, 2, and 3. But I figured if I printed that for you, that would be a great resource, and it would help us finish notes today, life goals for us today, and then we'll start homework in class. Assuming I can actually get this done. Okay. All right, so as a quick review, so go ahead and stop working on multiple choice if that's what you're still scoring or putting on your Scantron. As a quick review, talk in your groups if you've not already about the two solution processes listed up here, and maybe figure out if which one is endo and which one is exo based on your memory. So which one's a cold pack and which one's a heat pack. You need a buddy to talk to. All right, I need a vote here. Which one is endothermic? Ammonium nitrate or magnesium sulfate dissolving? Ammonium nitrate. That is like one of the very few endothermic processes that we have in a solution-based process. So you should know that is always going to be endothermic. That's an example of a cold pack. So what's the formula for ammonium nitrate? NH4 and O3. Okay, so if we have this and it's solid, and we run it through the solution process, we're just going to put water on top, because if we write water as a reactant, you will likely make it a double replacement reaction, which would be a chemical change, right? If we're talking about solution processes, is that chemical or physical? Physical, so we don't want it to look like a chemical change. So just put water on top to indicate that that's present, and then what does it break to? NH4 plus and NO3 minus. So we're making ions, right? And so in terms of this reaction, we have a delta H that is positive. What is the delta S of this? Are you questioning yourselves? Positive because why? Increasing disorder, right? Going from one solid to two aqueous ions. Those are definitely more disordered than the first. So therefore we put it as positive. Yeah. Memorization, essentially, for this one. We've been exposed to this before in our Hanover lab, and that, like I said, it's it's the few instances where a solution process overall. So memorize that. Just for ammonium nitrate. Sodium chloride is like very, very faintly endo, and there's a couple, like maybe a handful more, but most things are exo in their solution process. Speaking of exo, magnesium sulfate is going to be, so when we dissolve that, we have magnesium sulfate breaking into what? Water, sorry. Magnesium what? 2 plus ions, and sulfate 2 minus. Delta H is what? And delta S is, again, positive. So what are the two forces or the driving forces of reactions that we always have to consider? I heard somebody say it. Enthalpy and entropy. So a lot of times we're not given this information up front. We'd actually like to look to see, like, does the reaction occur? If it occurs, there's some sort of favorable driving force helping it occur. And if the reaction doesn't occur, then maybe the two driving forces are both going, thumbs down, sad face, not going to happen. What would both of those, in terms of both of these situations, what would the delta G be? Delta G, Gibbs free energy. Would it be positive or negative? Okay, I hear kind of both. Let's get louder and prouder. Why is it going to be negative? It's not really related to these values over here. If these two things are like legit processes that occur, they are occurring, therefore they are what? Thermodynamically favorable. We could say spontaneous, but we want to try to use the right terminology. So delta G for both of these is going to be negative, because they occur, and they occur under the conditions that's present at, like, let's just say room temperature. So the delta H and delta S and the temperature all agree to help delta G become negative overall. So if the process didn't occur, we would say delta G is what? Positive, no matter like the situational details. Quick review of thermochem. Okay. So we're talking about solutions. So we're talking about IMFs and how it plays into making the solution a solution. A lot of our solutions are going to be aqueous based. So we're talking about water. And you can definitely see the particulate diagrams come back into play a little bit. Okay, so what IMF, can you guys see this one right here? What IMF is coming into play right here when this negative ion is surrounded by waters? Ion dipole, right? So now we're actually using that IMF as it applies in the solution situation. And so in terms of our solutes, that's our solute, like sodium chloride. Our solvent is water. When they come together, they make a solution. There's a lot of solution energetics like delta H 1, 2, and 3 that we have to discuss. You read about it some in your readings. Let's just kind of make sure we can verbalize this. Okay. So we know it's ion dipole. That's at play here. So I've printed. Yes, I did print this for you. If you want a highlighter, they're right behind Christian in a pink box. If you want to star and add some detail, make sure you do that, especially the points I'm emphasizing, so that I know you're not zoning out on me. It's really I want you to interact with whatever you're doing. Okay. So if we're talking about solutions, we're talking about a lot of times ionic solution or ionic substances being dissolved in water or dissolved in a solution. And so we know that not every single ionic compound dissolves, right? Not dissolves well. So like if we have a precipitate, it's not dissolving well. Well, why? So if it's a precipitate, it's an ionic solid, right? So do you want to say IMFs are strong? Think ionic. What's holding it together? Okay, fluid attraction is really broad, but what's the energy associated with an ionic substance? Lattice energy, right? So lattice energy is really strong. The water molecules are trying to come around it and give it some ion dipole attraction to pull apart. But in that case where we have precipitate forming, a lot of times the lattice energy is so strong compared to those ion dipole forces, it's not going to break it apart. But we also have things that are going to be soluble, they are going to break apart, they are going to be overcome by this strong ion dipole attraction. All right, quick review of these IMFs, which is the strongest? We have, okay, so number 1, and that's because of the positive, I'm just going to use a cation for example, because of Coulomb's law, we have like maybe a positive ion like sodium interacting with a partial negative of water. That is a bigger number, magnitude, relating to a greater force of attraction. What's the next strongest? Hydrogen bonding, and that's because we have a big partial negative and a big partial positive attracted to each other through the very, very polar molecules we're dealing with due to their greatest electronegativity differences. And then next is who? Dipole-dipole. They're moderately polar molecules. They're still polar, so they still have a somewhat partial negative and somewhat partial positive we're dealing with. These are supposed to be smaller than these. I'm trying to just make my pictures bigger. And then lastly, London dispersion. And then what would I be drawing here? Partial negatives and partial positives? Yea or nay? All right, so normally we're like, hey, dispersion is happening with what kind of molecules? Nonpolar, but we then say electrons are polarizable and they create a temporary dipole moment, a temporary polarity to that molecule. But it's, it's very transient, it's here and there and here and there. So it makes a really teeny tiny partial negative and partial positive that's temporary. And that's what's going to cause that really weak London dispersion force, which is very easily overcome by heat or looking at it. All right, so that's a quick review. Yes?
Can you explain polarization?
So here's a molecule with 1, 2, 3, 4 electrons. Here's another one with 1, 2, 3, 4 electrons. Evenly distributed out. Let's say those are nonpolar. And so what happens is there's really no rhyme or reason why. Just because electrons can move, they can move, and they can create just a really quick asymmetrical distribution of charge. So for a hot second, if this one moves over here, and it's next to this one, we then have kind of an area on this side of the molecule that's going to get a temporary partial negative. Well, once that happens, and this side over here, due to the lack of electrons, because it's polarizable, they're able to, the electron cloud's able to kind of shift and be skewed in its symmetry. this letter here will then naturally gain a partial positive. So when this bumps up close to another one, it's going to be the positive side coming up close to this left side of this molecule. It's going to force this one to move and create a partial negative and a partial positive. So it's like a domino effect, but as soon as this electron moves back, the polarity ceases to exist, and therefore this one will, and this one will, and this one will. That's why it's temporary. Yeah. Only with nonpolar substances, yeah. Yeah. That is what that is called. Temporary dipole moments is the same as induced dipole. Sometimes you can induce a dipole with another polar molecule, so it's not like specific to a situation. You can also induce dipole by the nature of something being polarizable. Yeah.
So what makes something more polarized?
More electrons, bigger radius, like that's what you were explaining yesterday. Neon versus xenon. Okay, we're not looking at valence electrons, we're looking at total electrons. What is that? 10 versus more than 10. So you have a more polarizable xenon, which is going to have a greater London dispersion force, higher boiling points, etc. Total electrons, yeah.
So are induced dipoles different than just induced dipole?
So you can induce a dipole with a polarizable molecule, a polar molecule, or an ion. So you can induce a dipole with many things. Okay. All right, good questions. Any more here? Awesome. Okay. So when we're talking about solubility, we're talking about things coming together and interacting. So we just need to know that there's two things that help or control solubility. Specifically, the type of intermolecular force at play is going to help us say if something's soluble or not. What's our general rule of thumb? My favorite video of all time. Thank you, light dissolves light. Polar and polar. Oh, did you guys forget? I'm sorry. Did you already forget this? Because I can't live with this. I made my husband watch this last night. I'm Googling like a 5-year-old. Hold on. Hold on. I got this. Mark, what's your name? It's not Zuckerberg, is it? No. What? And oh my gosh, where's that? Yes, right there. Okay. What's his name? Roxenberg. Oh.
We saw you. Great. Now we're gonna get sued by ACT.
It's all relevant. It's videos, so watch the whole thing.
The salt is up in water in a beaker today. The ions broke apart in the usual way. The molecules of water kept the ions apart. A salt solution formed, but that's only the start. Homogeneous, same throughout. Homogeneous, same throughout. Solids that are polar can dissolve solutes that are polar or ionic. That is really cute. Water and nonpolar solutes just won't mix, but a nonpolar solvent like an E can fix. Like dissolves light, polar and polar. Like dissolves light, nonpolar and nonpolar. And all the solvent molecules used up and are stuck with the solute ion in your cup. Solution saturated, it is full for sure. Solubility's been reached for that temperature. Saturation on the line. Saturation on the line. You distill some water molecules unstuck, then more solute can dissolve. Hey, you're in luck. Solution is unsaturated, can't you see? You haven't yet reached the solubility. Unsaturated. Put more in. Unsaturated. Put more in. If you put more solute in, then can be dissolved. Then a supersaturation situation's involved. The aqueous falls out as a precipitate. Well, the solution is unstable sodium acetate. Supersaturation. Supersaturation. A salt that's out the water in a beaker today. The ions broke apart in the usual way. They made it harder for the water boil to freeze. So the patient temperature changes a few degrees. The negative property is concentration. The negative property is concentration. Electrolytes are the greater effect on the melting and boiling point of the solution than non-electrolytes. More solute that's dissolved got more effect. Solution's boiling point increases direct. The freezing point decreases, which is really nice. In the winter, salt on road to prevent the ice. Add a solute, boiling point goes up. add a solution for you now. That is wicked cool. Solutions rule.
I have probably see Mark. You know, it's a long last name. You could see how I thought Zuckerberg. Okay. Okay. So basically, polar is all polar, non-polar is all non-polar, and then the polar and non-polar mix. Can they mix? Yeah, they can. If your molecule has a hydrophilic and a hydrophobic end, it definitely can mix still. Whenever we are mixing, the big deal about why this is favorable to the universe and creates a more stable environment is because every single time you mix a physical system together, it should be lowering the potential energy. So that's important to know. And with relationships to energy, we always try to incorporate entropy as well because it's the third law of thermodynamics. So we should know that this is also going to increase the entropy of the system, which is going to tell us that it's a thermodynamically favorable process. Okay, so both of those correlate to making a thermodynamically favorable process. So neon and argon, they're not going to stay in separate chambers. Upon removing a barrier, they will mix. They won't stay in separate areas unless their densities are so different they just won't mix. Okay, so we should know the factors that will control solubility or control dissolving. One is the like dissolves like rule. We also need to explain that. So if you ever mention something's going to dissolve, you can say, yeah, the rule's like dissolve like. You can't say that on the AP exam. You must say, these molecules have similar intermolecular forces. Therefore, they will interact. Hence, dissolve or become soluble or something like that, okay? So make sure you're using your big boy words and not just saying like dissolves like. Miscible means what? Mixable, right? Basically means it will mix. And then we should know these groups, and this is important for a lab you guys are going to do next week. Your hydrophilic, what's hydrophilic mean? Hold on. Hydrophilic likes what? Likes water, right? So hydro means water. Philic, like you're a philanthropist, you give things, you interact in a positive way. So this one likes water, okay? So these are definitely the polar subgroups. Polar subgroups or polar functional groups. OH is a what? Alcohol group. C double bond O. H is what? It's on the end. Remember?
Aldehyde.
Aldehyde, like your hide. It's on your end. Okay. C double bond O, like in the middle. Ketone, right? So alcohol, aldehyde, ketone, C double bond O, OH. Starts with a C. Carboxylic acid, like acetate has a carboxylic acid group on the end, or acetic acid has a carboxylic acid group on the end, and then NH2 is a amide, yeah, or an amine. It's amide and amine. They're very similar in how they're structured. So all of those basically have polar areas on them. Therefore, they interact with water in a very nice way because of the similar IMFs, be it dipole-dipole or hydrogen bonding. Then you have those hydrophobic, like I'm scared of water, E, scared of water. Those are going to be your nonpolar groups. So this is literally just a nonpolar group, meaning it's a carbon chain with no other functional groups, which makes it overall a nonpolar structure. So we talk about these separately, but then we have to realize that we have really big molecules we deal with, and with those big molecules, we can have areas that are polar and areas that are nonpolar. Those would be like polymers, enzymes, food coloring, anything in life, hormones. Basically, everything has a polar and a nonpolar region. So your hydrophilic and your hydrophobic parts can interact in different ways with different solvents. So think about like who takes a multivitamin? Okay, who eats food with vitamins? Okay, so if you had a medicine or a vitamin or food that was, heavily fortified with vitamins and minerals or iron, you would need to eat it or drink it with certain things for it to absorb in your body well. So that's why we have like water-soluble medicines and vitamins and fat-soluble fat-soluble vitamins, minerals, etc., because they're going to be interacting with different regions of your body. So if you want it to absorb into your gut, it's going to need to be water soluble, but if you want it to absorb into other parts of your body, it needs to be fat soluble. So certain things are going to interact with different parts of your body based on their solubility. So there is a competition constantly between water and other things. So we definitely they have to basically prescribe you specifically what to drink with milk or to drink with water if we're trying to make like a vitamin or a certain medication travel to different parts of your body. Okay, so there's my video. I already showed it to you guys are good. But a lot of times we talk about solubility with reference to solutions, but we also know we can have solubility in any phase of matter, solids, liquids, and gases. So gas solubility, that means like a gas dissolving or blending with another gas. Gases are weird because they float away, so they need to be generally the same molar mass or the same density for them to actually mix, okay? So how do we publish gas density? What units? Grams per liter, right? So if we have some things that are similar in density, they will mix. If they're not similar in density, they won't mix. Liquids, this is kind of what we've been dealing with so far. We've been looking at like the polarity of molecules to determine if they're going to dissolve or blend. And then solids, we don't generally think about this, but if you make an alloy, they need to be similar enough to blend. If not, like say their densities are incredibly different, they're going to separate out just because the nature of how density works. The heavy things will sink, the lighter things will float. So density comes into play here. And also the characteristics they carry, which is kind of like polarity. It really is. I'll kind of relate that there. We call it ionic character, but the more ionic the character, the more likely it is to interact with others similar to it. And some good examples are like minerals like that make my favorite gems. Okay, feldspars are a mixture between potassium, sulfur, and sodium. And so these all kind of come together to make different types of ionic compounds, and they're going to be soluble within each other in their ionic nature. So just basically that we have things that can dissolve, not just liquids, but they can be gases or solids. This is not really a fun fact. Like, we should definitely know how soap works because we use it every day. It also relates to everything we're talking about now. Soap is a surfactant. Who's ever heard that word, surfactant? So it's basically helping break through the surface tension caused by water. So if you have oil like on your clothing and you put it in the washer just with water, it's not going to really come out. It's not going to do a good job. Because what's the water going to do with the oil? Just kind of repel, right? It's not gonna mix very well with the oil. So, or grease or whatever else could be on your clothing. So we add soap or surfactant to basically break the water tension, break the water's intermolecular forces, and we force it to interact with the nonpolar species, or like things like oil. And that's because it actually helps bring, it's like a little, like making them hold hands. It's bringing together the polar region and the nonpolar region to make them interact. So I thought this picture would actually be better. So this is a surfactant, like soap, and so it has a hydrophilic region, which is going to interact with water, and that's kind of like maybe like a sulfate group or something like that. So that ion can interact with water really well. And then this little chain, remember how we draw carbon chains like zigzags? That's a nonpolar region, so it's hydrophobic. Therefore, you can see that it's making a micelle. It's making a little area where all the nonpolar regions are clumped together so that they're kind of interacting in a positive fashion with each other. And they put their polar heads on the outside to interact with water. So as the soap does that, it interacts with the oil or the grease or whatever it may be, and it carries it away down the drain. So because soap has a polar and a nonpolar region, it can make things that normally wouldn't dissolve in water be interacting with water in a way that kind of cleans clothes in your hands and body, whatever else. There's something else I was going to tell you about that. I forgot what I was going to tell you, but I think, oh, this is like your cell membrane. What's your cell membrane made of? Phospholipid bilayer, right? So you've got the little phospholipid head, or phosphate head, the little bilayer, or two little lipid tails, and it does this over and over again, and it's a bilayer, so it does this on the other side too. And the reason it does that is because we want the cell to interact with water, because most of your body's made up of water, so they put the phosphate heads on the outside and the hydrophobic tails on the inside. Okay, now we're to the part where we actually like have to know the definite process of solutions. You guys okay? But so far, review a lot of review. Okay. So we know how solution processes have to occur. Sometimes we don't think about like the intermediate details, but this is where those details come in. So we talk about solution processes having in 3 steps. When you break apart solute molecules and then separately break apart solvent particles, then, only then, can the solutes and solvents interact. So we have to take it in 3 steps. So we call this one delta H. 1, we separate solute molecules. So in terms of solutes, give me 2 examples that we could call a solute. Keep it simple. Sodium chloride. What would we have to do to break that apart? Overcome the what? Lattice energy, right? So if you're a bond sodium to chlorine and you have to overcome lattice energy, would that be an endothermic or an exothermic process? Endo, right? Karate chop, like you're breaking the bonds, right? Same thing would kind of have to happen if you had carbon dioxide molecule next to another carbon dioxide molecule. You're not breaking the carbon dioxide molecule itself up, but you're breaking this, which is it's IMF. What IMF is that? LDF, because it's a nonpolar molecule. So we would still have to overcome the LDF forces, which again is going to require energy. So we should definitely know delta H1 is always going to be endo. Very similar situation, but regarding solvents, delta H2. For us to separate a solvent molecule from another solvent molecule from another solvent molecule, again, we have to overcome IMFs. What's the most common solvent we're dealing with? Water. So if water is next to water, they're interacting how? Hydrogen bonding. So it does take energy for us to overcome that. And if we had a nonpolar solvent, we'd be interacting or overcoming LDFs. So again, those have to be pulled apart, so it's going to require energy. So far, is this favorable to the universe or not favorable to the universe? Not favorable. But we know solutions form, so overall there must be a favorable aspect to this. If not, we would never be able to make a solution ever, because it requires so much energy, which is just not favorable. Delta H positive. So this is where we talk about those IMFs that pull together solvents and solutes. Oh, everything's moved. So this is where we talk about the delta H of the solution as a whole, and how it's a combination of solute particles being overcome, solvent particles being overcome, and then the like superbly exothermic process of solvent and solute interacting. So what happens when ions interact with water? What IMF is coming into play? Ion dipole, and remember that is super strong compared to all the other IMFs, which are relatively weak. So that's a very, very, very stabilizing process. And stabilizing and lowers the potential energy of the system. Delta H is negative, yada yada, super, super favorable to the universe. So what we're basically saying is that delta H3, being as exothermic as possible, can be so exothermic that it overcomes the 2 endothermic processes here, making us overall see a delta H of what? Delta H of solution of what? Negative. That is the most common example. This is so large, the interactions are so favorable and stabilizing, it causes, it's more than the delta H1 and delta H2 summed together. So, but we still can see a delta H solution of positive. What was the example we used earlier? Ammonium nitrate. So if that's still occurring, we still have entropy to consider as well. And so there's the examples, H1, H2, expanded solutes and solvents, making room for interacting, and then they interact. So they've put they have put a picture like this in the AP exam before, and you had to explain kind of what was happening or indicate the exothermicity or the endothermicity of each process. Okay? So maybe start that. I have a question on here. Quick thought. Would the delta H2 be greater for water or for benzene? Why water? So remember when you explained, you mentioned both, right? So water has what IMAFs at play? Hydrogen bonding, and benzene would have what? The latest version. What's benzene look like, guys? It's a what? It's not circle.
Like a hexagon.
Hexagon. Circles and hexagons are different. So it looks like this, which is going to be carbons all the way across, and so it's non-polar. And therefore, that would give us the LDF at play. Okay, so yes, delta H for water would be bigger because of the incredibly strong hydrogen bonds. Okay. Okay, so this is what's happening. Attack of the killer water molecules. They're coming into the ionic structure. They're pulling apart. What is the bigger ion? Why the anion? As you add an electron, the electron cloud repels other electrons and it gets bigger. We got that wrong on the extra credit. I just want to review that real fast. Not we, some of us. But the little purple small one would be the what? Cation. Okay. What part of water is attracted to the anion here? Hydrogens. And then what part of water is attracted to the cation here? Oxygens. And then we can attest to you. How did all my honors kids draw water? They draw it as HO2. I do. And then you guys did too, because you think to yourself, oh, H2O, you're thinking two O's. No, H2, two H's. So we're getting better, but you can definitely tell about some honors chem if you wish. Okay, so again, this is the key part, and this is like basically telling us why processes like this occur. If your solidation process between ionics and water are occurring, it's because it's super low or lowering in potential energy because of this attraction that's occurring between ions and water. That attraction again is called ion dipole. Thank you. And this happens, I don't think you guys probably saw this, but this is happening 6 times. 1, 2, 3, 4, 5, 6. There's 6 water molecules around each ion. And so because of that 6-fold increase in attraction, that's really the reason why it's very stabilizing. So you should know that most of the time each of the ions are hydrated 6 times, meaning surrounded by 6 water molecules. And this last piece down here, we've already mentioned it once, but if delta H3 is less exothermic than H1 and H2, what will the overall solution delta H be? Positive, so will the reaction or will the solution process still occur? Say again? Possibly, right? What would we have to consider? Entropy, right? Right. Does it increase entropy enough to allow for the positive delta H to still exist, but to still yield us a negative delta G? Got me? Relationship between delta H, delta S, and delta G. Oh, yeah. Okay. How much of this do I need to go over? Let's skip that one. Okay, nope, skip this one too. Alright, go to this. This is on your slide, I believe. This is a good enthalpy diagram of a solution process, and really I want to make sure you can explain each part. So, in your group first, discuss what each arrow is representing, and then try to answer this question here, okay?
That energy decreases in the becomes 8 because that's going to K acts, so K plus aqueous minus aqueous. So when the energy is needed, then the other arrows from the K plus K
Alright, so I'm going to point to one. I'm going to see if you can explain to me why the number is what it is, or the sign is what it is, and hopefully give me some indication what's happening here. So this process here, that's the downward facing arrow is representing what about the process? Is it endo or exo? Okay, so the downward facing arrow is definitely exo, and then you can see the label here is exo. What is happening here? We're calling it delta H of hydration, which should give you a clue. What's happening here to make this a negative 819 kilojoules per mole?
The gases have to mix with like water to make it increase.
So we call these gaseous ions because of the definition of lattice energy. So you're saying the what's interacting with water, not the, don't say the gas.
The gaseous ion.
The gaseous ion, really it's just the ion, right? So the ion is interacting with water. Okay, keep telling me more.
And so it's taking more energy to like calm them down into like the aqueous ion.
So it's taking energy.
Because there's a lot of kinetic energy, so it has to release that kinetic energy to become like an aqueous ion, maybe not, okay?
No, I think you're reading into because when you're talking about taking energy, to me that sounds like you're saying you require energy.
No, they're releasing energy because they're like wild child.
Wild child,
They
okay.
have gaseous ions, you know?
Alright, hold on. Go back here and don't think too hard. What is happening between the ions and the water that's releasing energy?
They're overcoming ions.
Not overcoming ions, because then that would be us putting energy in. They're what? What interaction is occurring between the ions and water?
Ions.
What IMF?
Ion dipole.
Ion dipole. Hallelujah. Okay, so ion dipole moments are coming in, or ion dipole IMFs are coming into play. Remember with each ion, what did I say would happen with waters? Like this one is, okay, the big one is who? So who?
Oh,
Fluoride, right, interacting with 6 waters, that's 6 ion dipoles, plus this one, which is K plus, times 6 waters, 6 more ion dipoles times a bajillion, whatever happens here within this lattice structure. So all of those ion dipole moments forming is very, very, very energy stabilizing, so it's energy lowering. Remember, any kind of bonding process, any at all, be it IMF, bonding, attracting, or literal bonding, it's always energy lowering. So that is a key point. Anytime you have attractions, it's energy lowering. This is quite energy stabilizing, so released 800 kilojoules of energy. But we have to compete with how much energy it took to even break the ion lattice apart. So what's happening here? Okay, so how much energy went into that process? Okay, a lot. Okay, so that's the lattice energy between potassium and fluorine. And so the attraction that we had to overcome there was the lattice energy, which was 800-ish kilojoules per mole. So we call that H of solute, or the lattice energy, or the H of crystallization, which is actually the opposite of lattice energy. But it's basically talking about the energy of the crystal. So you can call it a lot of things, but it's just the energy of the crystal. And this is the energy of the solution process, of the IMF process. So these two compete, but overall, the delta H of solution, which is the summation of, in this diagram anyway, H of solution is equal to delta H of lattice energy plus delta H of hydration. Overall, this process is what? Endothermic. Yet again, we have to consider how entropy plays into this. And so this is a highly increasing of disorder, therefore this process likely will still occur. And we know it does because we dissolve ions in water like this before. Okay, can I move past this diagram? Yes. We have to have some data, truly, because we don't always know the energetics of solution process, but I can always have you imagine that a lot of times about precipitates, solids are still there, so it's not increasing entropy a lot to cause overall thermodynamically favorable process. Therefore, we would see very, very little ions form. Okay. Okay, I'm going to have you guys read over this a little bit more. Star 2, these 2 slides I skipped because a lot of it's in your reading, and it's just me going over solution processes again and again and again. The only caution to you on that is, do note they call delta H 1, 2, and 3 different things sometimes. So delta H1 is usually referring to the solute. Delta H2 is usually talking about the solvent breaking apart. Delta H3 is talking about the attractions. So be it delta H hydration, which is like literally talking about the attractions, or delta equals line synergy, which is talking about the solute. Just note sometimes the words change, and I can go over more of this next week. This is kind of the boring part. Okay. Okay. If you can each of your groups come up with one example of a solution between a solid and liquid, solid, solid, liquid, liquid, gas, gas, and liquid gas. Try not to look at my little cheat sheet I provided there for you, okay? Come up with examples first. You probably can't even see that chart. But yeah, it's still solid. So don't look at my little chart I provided you. However, the little chart I provided you.
No, it's carbon. Maybe it's
That will be what most of these. All right, I'm gonna point to each group. Give me one, okay? Your choice. Your choice. Solid, liquid. Front group up here.
NaCl.
So salt water. Okay. I'm just put NaCl, aqueous. Okay. Front group. Solid, solid.
Steel, so it should be like
Oh,
iron.
good. Yeah. So an alloy. Steel. Steel. I had a teacher spell. They called themselves Mr. Steel, but they spelled it that way. It's hard to forget that.
So,
Alloy. Okay. Liquid. Liquid back table. Okay, so let me get one more of those because there should be so many examples floating around in your guys' head. You guys have a liquid, liquid? Oh man, back table.
gasoline.
Gasoline would be a good example because it's a mixture of many liquids together. It's not 100% like octanol, right? What about like what's vinegar made of?
Acetic acid.
And vinegar, and water, right? Vinegar would be acetic acid in water. What is like grape juice made of? Grapes would be a solid. So grape juice and water, and they lie to you. There's like plums in there, and cranberry juice and apple juice. They put all kinds of juices together. Okay. Okay. Gas. Our air, thank you, our atmosphere is made up of many, many gases. Liquid gas,
Carbonated drinks.
carbonated beverages. Anything else? Okay, so DO in water, dissolved oxygen in water, ocean water. Okay, let's do that. Yeah, it's a pretty good list. So basically, you know that solutions can form, and they're homogeneous because you cannot see the differences between them. Homogeneous just means that it's uniform throughout. And then you guys can see on the bottom, there's more examples you guys can preview on your own. Okay, who's pretty comfortable with these curves? What are these things called? Solubility curves, okay. What's common for most solids, no matter if they're ionic or covalent? What's common for most solids? Increasing solubility with increasing temperature, right? So is that a direct or an indirect relationship? Direct. What does the line represent?
The saturation.
On the line. Saturation. Remember that from the video? Okay, I know this like by heart. It's hard to not say it out loud. Okay, so saturation on the line. If I'm above the line and I had like sugar and I put at 20 degrees, I put 260 grams in 100 grams of water at 60 or at 20 degrees, what would my solution be called?
Super
saturated. Precipitate, yeah, so that's super saturated. And it would be like a false hope in keeping all that in there. So if you're making sweet tea at 20 degrees Celsius, it'd be pretty cold, and you put that much sugar in, it would fall out of solution. It would not hold in that solution very well. And if you put potassium nitrate and you only put whatever that is, like 110 grams in at 80 degrees Celsius, what kind of solution would you have made? Unsaturated, not undersaturated. So 3 types of solutions: supersaturated, saturated, and unsaturated. Okay, common theme for all gases. So solubility decreases with increasing temperature. Therefore, this would be a direct or an indirect relationship. Indirect. And the reason this occurs is because as you add temperature to gases, what happens? As you heat up gases. Okay, their kinetic energy is increasing, so they're in a solution, right? They're little gas particles, their kinetic energy is increasing. What are they doing? They're what? Yeah, they basically move. They hit the surface, they're like, oh, pop out. Because as they hit the surface, they're the only things that have a high enough vapor pressure, have a high enough energy to come out of solution. And that's assuming that they're in an open system that could occur. Because, you know, if you had a closed system, the bottle or whatever would explode because the gases would come out and then it would just like, because their pressure would be so high. Yeah, so I've heard somebody else talk about IMFs. If you have high kinetic energy with gases, they do pull apart from their IMFs quite easily, so that's another reason they can hit the surface and go. And yeah, okay. And no. Okay, let's hit this and then I'm going to have you start for a second on your own. And this is all mostly reviewed from honor chem, molarity units or whatever, what? Moles of what? Moles of solute over liters of solution. That is a key, like, there's some key differences between molarity and molality. So that's why I have that there. All right, so then molality, right, is lowercase m. And some of you guys maybe didn't calculate this in honors chem, but it's related to our chelated properties. We're talking about on Monday, so that's why we are talking about this now. Molality is moles of solute over kilograms of solvent, right? So it's not solution here, it's solvent. So that's one of the big differences between those two. Mass percent, just like any percent, it's part over whole. So mass of, if we're talking about solutions, of course, it's mass of solute over total. And that would be solvent plus solute. And then mole fraction, do you guys remember this from gases? A little bit. It's just the part, again, it's part over whole. So mass percent is grams over total grams, where mole fraction is moles over total moles. So it's the moles of the substance you're interested in, of course, will be on top. We do not multiply that by 100. It's unitless, and it's usually a decimal, and that's fine. This we do multiply by 100 to give it a percent look. Yeah. Let me see where we are on this with an example, and I can go back and elaborate more as needed. Is that okay? Okay. So go to this one, which you can write on that paper if that's what you're doing. And I will go back and talk about some of those other solution-based ideas that we need to know. All right, so determine the concentration of each. Remember, all of those examples I just went through, all of those are considered concentrations. Molarity, molality, mole fraction, and percent, mass percent. Those are all considered a version of concentration. Concentration does not only mean molarity, but that is our most common and favorable unit of all. All right, so solutions prepared by dissolving 25.0 grams of magnesium chloride in enough water to make 450 ml solution. Calculate the molarity, and then down here you can see you're asked of more. Go ahead and talk in your groups and let's go.
Oh, sorry. It's like 94. It's 35 plus 35. It's like 1.
You're working on number 2 after you're done with number 1.
Yeah, that's right.
Yeah, you'll notice I have a dot on mine. Alright, good question. How do you figure out who's the sole Ute and who's the sole Lynn? What's going to be your most logical answer here? Whoever is lesser is the sole Ute, right? The lower number is going to be important, or it's going to give you the sole Ute because it's mixing the bigger amount of solvent. Lower by mass, moles. It's got all that give you. Milliliters. The lower number is going to be the sole Ute. Like that earlier, I can look there and say who's the sole Ute immediately. Hexane. I mean, sorry, decade. I was reading because it was next to it. Yeah. So this is your smaller amount. And so that's why I said you can go by grams, by milliliters, by moles. That's about all the really universal units.
Did you do the bottom? Yeah, Yeah.
You're supposed to be doing this on your own, looking at your own stuff. Hold up, you can check your work in a second. If you get stuck, I get it, but work through your groups. Mass fraction. All right, let's make sure we didn't make any calculation errors, including me. Ready? Molality. Actually, let me hold on. I think anytime you have like 3 or 4 questions like this, you really should just get your moles for both, and then utilize those. And it would be very, it would behoove you to circle the moles so you don't lose it in all this work because it gets lengthy. So both your moles, give me a quick check. Hexane and decane, do we get approximately the same?
Yes.
All right, so then it depends on like how many sig figs you use throughout your calculations as well. But then you're using for molality moles of decane, because that's the that's a smaller amount, over kilograms of hexane, which is your solvent, and then you should get 3.72 little m. That's how we denote molality. And then mole fraction, you should take your moles over your total moles. Moles of hexane, decane over total moles, 0.243. I think there were 3 sig figs all the way, because they were all given to you initially as 3 sig figs. Mass fraction, you probably figured out. It's just the same as mole fraction, but with grams. So we're taking grams of hexane over total grams. If you were to get mass percent, what would you have to do with this? Multiply 100, so you could get 65.4%. So far, so good? All right, so I feel like you probably we'll have time Monday to do the pre-lab aspect of our lab. So I'm just gonna hold off on that for now. Go ahead and open up your packet that I provided you for the day 1 practice. I do want to tell you one more thing, but I want to show you where this is first. It's going to be after the FRQs that we did last time, and after like one little set of notes that we will do on Monday. Looks like this: practice solution concentrations day 1. Okay, so I'm starting you off with lots of different scenarios, and you have to manipulate that data to then get yourself to the individual units of moles and mass to get whatever the question is asking for. So I'm asking for 1 through 5 to be done Monday, but I know that you might get stuck on one aspect of one of those. I won't tell you which one, but I want you to at least fight through for a minute and try it, okay? So the only thing that we have not mentioned that's on the board is density. Okay, you see grams per milliliter. Don't forget density exists, and that's the branch between a lot of things. Okay, so we haven't done one with density together, but I think you can figure it out, because the density is going to give you basically the bridge between mass and volume. So there's normally mass and volume. They're just 2 independent characteristics. Density connects them. So that's my only hint for you there, okay? So start in your groups if you wish. Please just on a separate sheet of paper or on the back, because I do not want to try to read like between lines, people. Don't make me read between lines. Whenever is it? You have all of them on there? Thanks. Are you talking about PES?
I remember I took notes.
Oh, yes. So, do you have that packet? Yeah. I'll show you what it is. Yeah. Okay. You have 10 minutes. At least get number 1 done. Let's go.